Have you ever stopped to think about how you can stream a movie from a server that's thousands of miles away? Or how an email can literally cross the planet in the blink of an eye? Well, it's not magic, it's pure physics. And the hero of this entire story is a tiny pulse of light zipping down an impossibly thin thread of glass. Today, we're going to follow that pulse on its journey and really master fiber optics. So here's our game plan. We're going to start with the absolute basics. What even is fiber optics? Then we'll get into the different kinds of fiber and the physics that makes it all possible. We'll also look at the real-world problems a signal faces, check out some incredible applications, and wrap things up with an exam corner to make sure you've got this stuff down cold.
All right, let's get right into it. To really understand the journey, you first have to understand the road it travels on. So what exactly is a fiber optic cable?
At its core, fiber optics is all about sending information, coded into pulses of light, through these super thin strands of glass. And these aren't just any old cables. They are the absolute backbone of our connected world. They're the superhighways that carry everything from global financial trades to your weekend movie binge.
Okay, now take a look at this. The structure is so simple, but it's absolutely brilliant. Right in the middle, you have the core. That's our highway where the light pulse actually travels. It's wrapped in something called the cladding, which has a slightly lower refractive index. Now, you can think of refractive index as kind of like the speed limit for light, not material. So the cladding has a higher speed limit than the core. And that difference? That's the secret sauce that makes everything work. Then you've just got a protective coating on the outside to keep it all safe.
So that leads to the big question, right? You're shooting a beam of light into this tiny glass thread. How on earth does it not just leak out? How does it stay perfectly contained on a journey that could literally stretch from New York all the way to London?
The answer is this amazing principle from physics called total internal reflection, or TIR for short. Because the cladding has that lower refractive index, the boundary between the core and the cladding acts like a perfect mirror. As long as the light hits that boundary at a shallow enough angle, it reflects perfectly, bouncing its way down the fiber with almost zero loss. It's the golden rule of the road for light inside a fiber.
But, as it turns out, not all of these light-carrying roads are built the same way. The journey for our little light pulse can be totally different depending on the type of fiber it's traveling through.
So the two main flavors are single mode and multi-mode. Single mode fiber has a ridiculously tiny core. We're talking 8 to 9 micrometers. That's smaller than a human hair. This forces the light to travel in just one single straight path, or mode. This is perfect for long-distance communication because the signal stays clean and doesn't spread out. Multi-mode, on the other hand, has a much bigger core, which lets the light bounce around in lots of different paths. It's great for shorter runs, like inside a data center, but over long distances, all those different path lengths cause the signal to get all smeared out.
And this visual just shows another brilliant design trick. Look at the top diagram, the step index fiber. You see that sharp change in the refractive index? The light rays that take those longer zigzag paths are going to arrive later. But now look at the bottom one, the graded index fiber. This is so clever. The refractive index is highest right at the center, and then it gradually gets lower toward the edges. What does that do? It means the light rays on those longer outer paths actually travel faster. This lets all the different rays arrive at the finish line at almost the exact same time. It's a fantastic way to reduce that signal smearing we call dispersion.
Okay, so we know about the different kinds of roads. Now let's get into the traffic laws. We're going to dive into the physics and look at the actual calculations that tell us if lights can even get on this highway and, more importantly, stay on it.
You see, to make sure we get that perfect total internal reflection, we can't just shine light into the fiber at any old angle. It's kind of like trying to skip a stone across a pond. If you throw it straight down, it just sinks. You have to hit it at a nice, shallow angle. And as you can see here, there's a very specific launch angle that we care about. If that angle is too steep, the light will just refract right out of the core and be lost forever. So our job is to figure out the absolute maximum angle that will work.
And we can figure this out with some pretty straightforward physics. First, we use Snell's law, which tells us how the light bends when it goes from the air into the glass core. Then, with a little bit of geometry, we can connect that angle to the angle of reflection happening inside the core. After that, we just apply our golden rule, the condition for total internal reflection. And boom, we can solve for that maximum incident angle, which we call the acceptance angle.
So, all of that derivation boils down to this one super useful number called the numerical aperture, or NA.
You can think of it as a grade or a figure of merit for the fiber. It tells you exactly how good it is at gathering light. A fiber with a higher Na can accept light from a much wider cone, which makes it way easier to work with.
Hey, remember our chat about single-mode versus multimode fibers? Well, this right here is the master number that decides which is which. The V number basically rolls up the core size, the numerical aperture, and the wavelength of light all into one handy parameter. And here's the magic part. If that V number is less than 2.405, that fiber will only support one mode. That's it. It officially becomes a single-mode fiber. It's our official mode counter.
So far, our little pulse of light seems to be having a pretty good trip. But, in the real world, it's never a perfect journey. There are villains in our story, things that actively try to weaken and mess up our signal as it travels.
The two big enemies are attenuation and dispersion. Attenuation is just a fancy word for the signal getting weaker, or dimmer. This can happen because tiny impurities in the glass literally absorb the light, or because little imperfections scatter the light in all directions, or even because you just bend the fiber and let the light leak out. Dispersion, on the other hand, isn't about losing power. It's about the pulse spreading out and losing its nice, sharp shape.
Now, this is really cool. Attenuation is totally dependent on the wavelength of light you use. Check out this graph. Over on the left, at shorter wavelengths, you get a ton of what's called Rayleigh scattering. It scatters blue light the most, which is actually the same reason the sky is blue. Then way over on the right, at longer wavelengths, the glass material itself starts absorbing infrared light. So the sweet spots for communication are these valleys in the middle, these windows where the total loss is at an absolute minimum, and that is exactly where we operate our fiber optic systems.
And this shows you exactly what happens when you physically bend a fiber. It doesn't matter if it's a big, obvious macro bend you can see, or a tiny micro bend from some imperfection. The result is the same. That bend changes the angle the light hits the core clouding boundary. If that angle gets too steep, it breaks the rule for total internal reflection, and poof, the light just leaks right out. Here's that other big problem in action: pulse dispersion. So you send in these nice, clean, sharp digital pulses, your ones and zeros. But as they travel down the fiber, they start to spread out and get mushy. If they spread too much, they start overlapping with each other, and the receiver at the other end can't tell where one pulse ends and the next one begins. This smearing effect is the ultimate bottleneck on how fast you can send data. So, despite all those challenges, engineers have figured out some truly incredible ways to use this technology. Let's take a look at where this journey of light actually leads in the real world.
Besides just communication, fibers make for fantastic sensors, and we can split them into two camps. In an intrinsic sensor, the fiber is the sensor. A change in temperature or some physical strain on the fiber directly changes the properties of the light passing through it. But in an extrinsic sensor, the fiber is just a delivery pipe. It carries light to some external sensor and then carries the modified light signal back for analysis. And this slide right here, this is the whole shebang. This is the complete system. You start with your information, which gets turned into an electrical signal. A transmitter, usually a laser, converts that into pulses of light. That light then travels down the fiber optic cable, maybe for thousands of kilometers. And at the far end, a detector turns that light back into an electrical signal, which finally gets sent to its destination.
All right, we've covered a ton of ground, from the basic anatomy of a fiber all the way up to a global communication network. Now let's put what we've learned to the test and see how these concepts might show up in the exam corner.
So let's leave it with this final thought. It's pretty amazing when you think about it. Understanding the physics of how a single, microscopic pulse of light bounces its way down a thread of glass is what enables our entire macroscopic world of instant global connection. From Snell's law to the numerical aperture, every step in that light pulse's journey is what makes our modern world possible. Mastering that connection is what really shows you understand the power of fiber optics.